Howdy. This video is on hydrogen bonding. Hydrogen bonding is one of the most important intermolecular forces. Hydrogen bonding is responsible for many of water's unique properties. It is what keeps two strands of DNA together, and it determines secondary structures of proteins. After watching this video, you should be able to describe what hydrogen bonding is, identify when it occurs, and describe examples of it, and explain why the examples are important. Hydrogen bonding is a special form of dipole-dipole interaction. Hydrogen bonding is not covalent bonding. It's a little confusing. We say hydrogen bonding, but it's not a covalent bond. It's a special form of dipole-dipole. It's about 10 times stronger than typical dipole-dipole interaction. And so here's an example. We have hydrogen bonding in HF. So you have an HF molecule, another HF molecule. The difference electronegativity between hydrogen and fluorine is really pretty large. So that's a very polar molecule. And so you have a partial positive charge on the hydrogen, partial negative charge on the fluorine. And so that electrostatic interaction is what we refer to as the hydrogen bond. We have it as dashed line, but it is not a covalent bond. It is just an electrostatic interaction. Hydrogen bonding exists when X and Y are fluorine, oxygen, or nitrogen. And so these are three of the most electronegative elements and are relatively small. So the more electronegative X, the larger the partial negative charge, and the larger the partial positive charge. So hydrogen bonding occurs when you have hydrogen bound to fluorine, oxygen, or nitrogen. Molecules have to be polar. And so here you can have hydrogen bonding between two different types of molecules. Here we have water, here we have ammonia. And so we have the hydrogen bound to the oxygen, attracted to the nitrogen because that has a partial negative charge. Here we have methanol and water. And so this hydrogen is bound to oxygen. Both molecules are polar. And there's an attraction between the hydrogen and the water molecule. And again, often we'll use a line or a dashed line to represent the hydrogen bond, but it is not a covalent bond. And so in ammonia, it will hydrogen bond with other ammonia atoms. Ammonium ion cannot be involved in hydrogen bonding because it is not polar. Remember, if you have a center atom surrounded by the same type of outer atoms and no lone pairs on the center, then the molecule has to be nonpolar. For hydrogen bonding, you need both hydrogen bound to a fluorine, oxygen, or nitrogen, and the molecules have to be polar. And so in water, we have hydrogens bound to oxygen. The molecules are polar. We get hydrogen bonding. And if you think about the hydrogen bond is about 20 kilojoules per mole, the OH covalent bond is over 100 kilojoules per mole. And so again, the dashed lines represent the electrostatic attraction referred to as hydrogen bonding. It is not a covalent bond. Now on ice, the hydrogen bonding is maximized, and that's what leads to this fairly open structure.
Ice is held together as a solid by hydrogen bonds. When ice melts to liquid water, the regular, relatively open structure of ice collapses. Liquid water can be more efficiently packed and denser than ice.
And so it's kind of interesting. The ice takes the form that maximizes the hydrogen bonds, which makes it a little bit less dense than the liquid water. Now, this is fairly unique for water. Typically for a compound, the solid will be more dense than the liquid. But for water, the liquid is more dense than the solid. And this is really important because in winter, this way the lakes will freeze on top, but not freeze throughout the lake. And so hydrogen bonding is why the liquid is more dense than the solid. Now this is a fairly decent simulation. You see that you start with the solid, the fairly open structure, and then as you add heat, the molecules move a little bit faster. And so remember, temperature is a measure of atomic motion at the atomic level motion. And so you can also think about phase transitions as a competition between intermolecular forces and kinetic energy. So initially, intermolecular forces are dominating. As we add heat, more kinetic energy to the molecules, eventually the molecules partially overcome intermolecular forces. So in both the solid and liquid, you have intermolecular forces, but in the solid, they dominate. You only have vibrations about the positions for the motion, but for the liquid, you actually get motion relative to each other. So when you're going from a solid to a liquid, you're only partially overcoming intermolecular forces. There's still enough intermolecular forces to keep the liquid together. And so water has a high boiling point because it has strong intermolecular forces due to hydrogen bonding.
A plot of the boiling points of the group 6A hydrogen compounds shows a trend. Based on this trend, we would expect the boiling point of water to be here. In reality, H2O's boiling point is much higher. This is a consequence of water's stronger hydrogen bonds.
And so it's kind of cool. We can look at these different compounds. This is going down the period, and on the y-axis we have the boiling point. And so we could ask the question, okay, why does water have a higher boiling point than H2S, H2SE, hydrogen selenide, and hydrogen telluride? Well, the water has hydrogen bonds. We could also ask, why does HF have a higher boiling point than HCl? And so HF is here, and HCl is right there. Well, again, HF has hydrogen bonding, HCl does not. Now, chlorine is more electronegative than nitrogen, but it's also bigger. And so when we'll talk about hydrogen has to be bound to fluorine, oxygen, and nitrogen, freaks of nature, because there are the three of the most electronegative elements. Fluorine is the most electronegative element. Oxygen is the second most electronegative element. I think nitrogen is the fourth. Chlorine is the third. There is no hydrogen bonding with chlorine because of the size. It's a little bit bigger than the nitrogen. Why do the following boiling points go in the increasing order? So we have SnH4, GeH4, silicon H4, and methane. And so hopefully you notice that all these are nonpolar, and so that would just be London dispersion. And so I really like this plot because it shows you the two things. It shows you here on the left, this is due to hydrogen bonding, right? So water, HF, and ammonia all have hydrogen bonding, and so all have fairly high boiling points. And you see that as you get to more massive molecules, you're increasing the boiling point. And shows you that for London dispersion, the higher the molar mass, the stronger the easier to polarize, stronger interaction, and the higher the boiling point. So this plot shows you both about hydrogen bonding and about London dispersion. So which has the highest boiling point? Methane, water, or helium? And so remember, the goal is to figure out what are the intermolecular forces present. And so typically you have to draw the Lewis diagram. And so for methane, you'd see that was nonpolar, so the only interaction is London dispersion. Water has hydrogen bonding and London dispersion. Everything has London dispersion. And then helium's a noble gas, it has just London dispersion. And so that means that the water should have the highest boiling point. Now between the methane and the helium, the more massive has easier to polarize, stronger London dispersion. And so methane is more massive than helium. And so helium should have the lowest boiling point. And water should have the highest boiling point. You could also be asked which of the following experience hydrogen bonding. And remember that for hydrogen bonding, you need hydrogen bound to fluorine, oxygen, and nitrogen, and the molecules have to be polar. And so for that first one, you have two hydrogen atoms bound to each other, but that is not what we mean by hydrogen bonding. When we mean hydrogen bonding, we're talking about intermolecular force, we're talking about the electrostatic attraction between the molecules. Water molecules will experience hydrogen bonding. HF molecules will experience hydrogen bonding with each other. Ammonia molecules will experience hydrogen bonding. Again, hydrogen has to be bound to fluorine, oxygen, and nitrogen, freaks of nature. H2S, while it's polar, it will not experience hydrogen bonding. So hydrogen bonding, very important intermolecular force, results in a lot of water's unique properties.
DNA is composed of two sugar phosphate chains that are oriented in opposite directions. This orientation permits complementary base pairs to be connected by hydrogen bonds. Hydrogen bonds are responsible for the helical shape of the molecule.
And so it's kind of cool. The two strands here are just held together by the hydrogen bonds of the base pairs. And if you have one base here, you have to have a specific base on the other side, and that is based on hydrogen bonds. And so if you have adenine on one side, you have to have thymine on the other side, and again, it's based on the hydrogen bonds. Here we have hydrogen bound to nitrogen and attracted to the oxygen. Here we have hydrogen bound to nitrogen, attracted to another nitrogen. Hydrogen bonding is also responsible for the secondary structure of proteins. And so proteins are very complex, very large molecules. And so often we'll talk about primary, secondary, tertiary, and quaternary structure. And the secondary structures for proteins could be what's referred to as alpha helix, or it could be a beta sheet, which it is that depends on the hydrogen bonding. And so it's kind of hard to see, but you have hydrogen bonding here, and that's what's resulting in the alpha helix. In terms of beta sheet, you have two strands of the protein, and then you have hydrogen bonding between them. So you have hydrogen bound to nitrogen, attract to oxygen, hydrogen bound to nitrogen, attract to oxygen, hydrogen bound to nitrogen, attract to oxygen, and that gives you the beta sheet. And so this is a crystal structure of a protein. Again, here you see alpha helix, beta sheets, more alpha helix, more beta sheets. But again, it's just due hydrogen bonding. So hydrogen bonding is one of the most important intermolecular forces. It's responsible for many of water's unique properties. It's what keeps two strands of DNA together. It determines secondary structure of proteins. It is just a special form of dipole-dipole interaction. It is not a covalent bond. I hope that was helpful.